Okay, welcome everyone. I hope you can hear me. I mean, would you say yes if you can hear me? Okay, good. So, okay, thank you very much. So yeah, welcome to this lecture 4 of this introduction to logic in computer science. So what we were going to cover today is some sub-fragments of propositional logic where we can have efficient polynomial time algorithms. So we will focus on satisfiability problems, but instead of thinking arbitrary Cnf formulas, we're gonna look at something called Horn formulas, 2 Cnf formulas, XOR Cnf formulas, and so on. And then we will show that for those kind of formulas, we have a polynomial time algorithms. So one high-level message I want you to come across in the, at least for first 2 segments, like a Horn formula and the 2 Cnf formula, is that these are very special formula where to check satisfiability, we don't need to backtrack, okay? Why satisfiability and validity check is, especially satisfiability check is hard computationally. One of the reasons is that it's like searching. In order to find a satisfying assignment for a given Cnf formula, you need to do backtracking. You can't really make one choice and then say, okay, this is the right choice and I will stick to it. And it's not going to work. But for Horn formula and 2 Cnf formula are special. So in these cases, by using some structure of these formulas, we can design an algorithm which doesn't have to do backtracking. So that's why we can have a polynomial time algorithms. XCNF, we're gonna talk about it, and then it's special because it's the case where you can use what you learn in a linear algebra. And finally, we're gonna talk a little bit about so-called work set, which is a randomized algorithm for solving satisfiability problem. And we will do some analysis of this randomized algorithm using and something, some of you may have learned from random walk analysis. Okay, so let me start with, so the big topic of today is computational aspects of propositional logic, especially some sub-fragments of propositional logic. And then before starting this, I want to remember a few things that we covered before. These are the concepts that appeared when we talk about this conjunctive normal form, okay? So all the formula we're gonna deal with, they will assume some form of, some kind of normal form, which will be either conjunctive normal form or something very similar. So in all of these cases, these concepts will appear, play a very important role. So first concept is literal. Literal is either propositional variable like x that you see on the screen, or its negation, okay? Propositional variable or its negation are called literals. And then we say the usual propositional variable as a positive literal, its negation as a negative literal. So these are the basic ingredients from which we're gonna build a more complicated propositional logic formula. And then from using these literals, we're gonna construct something called the clause. Clause is a disjunction of literals, okay? And then conjunctive normal form is a conjunction of clauses. So the CNF formula will have the form that we have a big conjunction outside. Inside the big conjunction, we have a disjunction of literals. And then this disjunction is going to be called clause. Each of these L will be called literals. The entire thing will be called the conjunctive normal form. And last time we said for this, if formula is given as a conjunctive normal form, checking validity is very easy. It can be done in polynomial time. But checking, we said satisfiability, at least it's not obvious. And then in fact, it turns out that it's a so-called NP-complete problem, which means it's as hard as, many of the well-known non-trivial computational problems, or or it's as hard as all the NP problems. Okay, and then I just want you to remind these two conventions. We said true is a conjunctive normal form which without any clauses. So in some sense, this true corresponds to the case where this outermost conjunct is equal to n is equal to 0. So we don't have any conjunct at all. And false correspond to the conjunctive normal form where n is equal to 1. So we have a single clause. That single clause doesn't have anything. So it's M1 is going to be 0. And this convention is inconsistent. I mean, this convention is inconsistent with the fact that true is a unit of conjunction, false is a unit for disjunction. Okay, so this is a reminder of some syntactic convention that we are making, but I mean, many of the set solver that we're gonna talk about, some satisfiability solver we're gonna talk about, and which you will also have to implement later. I mean, all of them, conjunctive normal form is going to be the input to the set solver. We're gonna have some encoding of this conjunctive normal form. And that's enough because, I mean, we will show at some point in today or maybe on Wednesday's lecture, having a good solver for conjunctive normal form, but especially 3CNF is as good as having the good satisfiability solver for all the propositional logic formulas. Okay, so then this is a big introduction. So what we're gonna cover today, I think we will spend most of our time today is to talk about polynomial time fragments of propositional logic, Horn fragments, 2CNF fragments, and then if time allows, we're gonna also talk about XCNF fragment. No, it's not fragment, but XCNF formulas. Then maybe next on Wednesday's lecture, we're gonna talk about walk set, which is a randomized algorithm for solving satisfiability. And as I said before, satisfiability is a hard problem, okay? And I mean, one way to see this is just to remember what you learned from algorithm course when you learn about so-called NP completeness, NP hardness, and so on, or polynomial time reduction in the algorithm course. I mean, you might have learned that satisfiability is one of the first so-called NP complete problem proved by Stephen Cook. And so this is the hardest problem in the so-called NP class of all the computational problems. Okay, so this is, and then another way to understand this, if you have no idea about what I'm talking about, is that if you just look at what you can easily design to solve satisfiability problem with the kind of algorithm you can easily design. One way to do it is to do the truth table. And you can see that the truth table, most of the time, it will take an exponential time. If you have 5 propositional variables, the size of the truth table is going to be 2 to the power of 5, which is, I think, maybe it's quite, I mean, then that number will grow exponentially as the number of variable increases. So the truth table method is gonna take most of the time, it's gonna take an exponential time in many cases, in most of the cases. However, as I said, there are some special fragments of this propositional logic formula have a polynomial time algorithm. And in fact, this fact has been exploited in the computer science in multiple different ways. So the first formula we're gonna talk about is a Horn formula, and we also talk about 2CNF and XCNF. Let's go to the Horn formula. Horn formula is a conjunctive normal form formula, CNF formula, where it satisfies one constraint, which is each clause, which is a disjunction of literals, has only one positive, at most one positive literals. So here's an example of Horn formula. Okay. Let me use pen here. So here's an example of Horn formula. There are 3 clauses. One is P1, the second clause is negation of P2 and negation of P3. The third is what you see here. And then now if you look at the third one, it has one positive literal, I mean this guy, and that's it. I mean the other literals it have are all negative, okay? The negation of P1 and negation of P2. So it satisfies the requirement for being Horn formula. The requirement is there should be at most one the positive literals. The second one it also satisfies the requirement. That's because it doesn't contain any positive literals. And the first one is also satisfies the requirement because it only contains one positive literal. But what you can note that it doesn't have to contain any negative literals at all. So just having P1 is okay. It meets the requirement of a Horn formula. Okay. So if you look at these conditions of the Horn formula as like the one like I described here, you might think that okay, this looks arbitrary and random. And in fact, actually that is not. And in a bit better way to look at some structure imposed by this constraint of the Horn formula is to rewrite Horn formula in terms of implications. So if you rewrite Horn formula in terms of implication and then write it as a so-called implication form, then the Horn formula is the one which can be written as an implication form, where left-hand side of the implication contains, either true or just propositional logic, propositional variable. Right-hand side is either false or contains one propositional variable. So you see that this P1 is the same as so P1 here is the same as this guy. That's because, this one is equal to negation of true or P1, and negation of true is equal to false, and false is a unit, so adding false or P1 is identical to P1. So P1 can be written as implication, where the left-hand side of the implication is true, the right-hand side is P1. This part can also be, it corresponds to the second clause that you see on the Horn formula. So, this, if you rewrite this is the same as negation. Okay, it's a negation of P2 and P3 or false. But then negation of P2 or P3, because of De Morgan's law, that's the same as negation of P2 and negation of P3. False is a unit, so we can kick it out. So that's exactly the same as before. So one general pattern you can see is that in Horn formula, we have a bunch of negative literals. They all go into the left-hand side of the implication and then they will all be combined using conjunction. And then write the unique positive formula, positive literal is going to appear on the right-hand side. If there's nothing, then we will put false here. So the most typical case is like the one that you see in the third. So maybe this is the kind of most typical case, and then that corresponds to the formula here. No, that corresponds to the the formula here. Then you can see that for all the negative literals appears on the left-hand side of the implication, and then they all get combined using conjunction. Positive literal, which is gonna be either exist only one or nothing, and they will appear on the right-hand side of the implication. Okay, erase all of these. Okay. So, and then this Horn formula has many applications in computer science. And as I said, especially the prolog and data logs are based on Horn formula. Prolog maybe doesn't have a big impact. Maybe or maybe not. But data log is much more prevalent in computer science. So if you look at database, data log can serve as a query language and also knowledge representations. And even sometimes if some people are working on the combination of logic and machine learning, they use some probabilistic models that are kind of closely related to data log. So data log, prolog play an important role, and they are all based on the Horn formula. And the reason they do this is because this Horn formula has some intuitive reading. At the same time, it has a very good computational behavior. Okay. So as I said, the Horn formula has a very good computational behavior, especially satisfiability problem for Horn formula can be done in polynomial time. So let me just kind of remind you of what this actually means. This means that we are thinking about computational problem where we are given a formula f, but we are assuming that that formula is a Horn formula. Okay. So we are given Horn formula f, and then what our algorithm has to do is we have to map this guy to either satisfiable, if this formula is satisfiable, or unsatisfiable. So that's what our algorithm has to do. So the input of our algorithm is a Horn formula. Output is either satisfiable or unsatisfiable. Satisfiability means that there exists some assignment to the propositional variable such that this assignment satisfies the formula f. So that's identical to satisfiability. Unsatisfiability means such an assignment doesn't exist. Okay, so this in general this isn't hard problem for Horn formula. It's not a very hard problem. Okay, why that is the case? And so the reason is that it's because it's because of the two reasons. In some sense, if Horn formula is satisfiable, then there exists the best satisfying assignment in some sense. Okay, I'm gonna make that what I mean by best much more precise by using this order so-called minimal model. So the high level intuition is that if Horn formula f is satisfiable, there is a best satisfying assignment. So then the design of the algorithm becomes substantially easier. What it has to do is it just presumes there exists the best satisfying assignment, and it try to find it. Okay, if it fails to find best satisfying assignment, that means there does not exist any satisfying assignment at all. If this formula is satisfiable, then our strategy of finding best satisfying assignment is gonna work. Because best satisfying assignment is always exist and unique, then we don't really need to do the backtracking. Okay, just to sum up, all the Horn formulas, if it is satisfiable, it has a very interesting property, which is it has a best satisfying assignment. So the design kind of high level, what we can do in terms of algorithm design is to design an algorithm that try to find that really go for this best satisfying assignment, assuming it exists. Okay. So now what do we mean by best? And that notion of best is captured by this order relation between the satisfying assignments. Okay. So we're gonna define the relation, this order less than, and for the model, which is an assignment, so which is a mapping from propositional variable appearing in F to 0 and 1. Okay, so that's what we mean by models. Or, I mean, we can, in general, this can an order that can be defined. So we are thinking about the assignments A and B, which maps propositional variables to 0 and 1. We say one assignment is smaller than another assignment B if the A as a mapping from the propositional variable to 0 and 1 is smaller. So if A of P is always less than or equal to B of P. So for instance, if A is a satisfying assignment that maps P1 to 0 and P2 to 1, and if B is a satisfying assignment that maps P1 to 1 and P2 to 1. So then by this definition, A is less than equal to B. That's because for P1, it map P1 to 0, and B maps P1 to 1, so 1 is greater than equal to 0. And the same thing happens for P2. So this is satisfy the requirement here. On the other hand, if we define C, which maps everything to 0, P1 to 0, and P2 to 0, And then this C is now less than equal, let me erase this. So this A is not less than equal to C. That's because for P2, yeah, so for P2, the A maps P2 to 1, but C maps P2 to 0. Okay, so we define an order pointwise. And then this order, what it say is that in some sense, B is kind of more truthful than A. I mean, you try to use more ones than B. And then B, you try to use more one than A. Okay, so now let's try to look at two Horn formulas and think about how we can go for designing some algorithm. One way to design if somebody asks you to check satisfiability of the first formula and satisfiability of the second formula, likely you're gonna do the following. Okay, so you will so what you will do is you look at all the conjuncts, and then because especially for Horn formula is given as an implication form, you will try to find some propositional variable that has to be true. So for instance, in both cases, the first conjunct, say true implies P1, which means P1 has to be true. I mean, this condition of this implication is always gonna be true. So P1 is gonna be true, okay? So we said P1 should be mapped to 1. Then now look at the rest. Because everything is written in terms of implication form, then this, by saying P1 is equal to 1, that activates, in some sense, the sum of the conjunct. So in this particular case, that's going to activate this third conjunct because left-hand side of the implication, the third conjunct is just P1. And then the P1 is equal to 1 means that now this assumption part is going to be true. So that forces us to say that P2 also has to be true. So that's why we say P2 should be true. Okay, so then the last case is though we have that's both happens for this. Okay, and then now at this point because the way this algorithm, and then usually we don't know what to do. Okay, we said, okay, P1 has to be true, P2 has to be true, and that's pretty much it. I mean, we can't really say anything further. So we can't, for instance, say this clause is not satisfied. We can't really say this because we know P2 is 1, but for P3, we can't say anything about this. But because of the minimality property, which I will show you later, it is okay, and that's how this algorithm actually works. It is okay to set all the other variables, so variable to 0. So for instance, if we set P3 to 0, and then check whether we can go anything further or not. So let me take it a bit back, okay? Because this makes it a bit confusing. So I'm talking about the first formula, and then I'm telling you how the satisfiability algorithm for Horn formula works. So initially, so I think this is a bit better. So I'm going to explain it again. Initially, say every propositional variable is 0. P1 is 0. P2 is 0. And P3 is 0. So just look at the first one. Okay. And then so you can see that this is the assignments, which is the smallest according to this order. So we start with the assignment that is the smallest according to this order. And then we look at how should we revise this. Well, when that revisions usually replace this assignment by something larger, okay, which means we replace either this 0 to 1, or this 0 to 1, or this 0 to 1. Okay, and then now if you look at the formula here, it says that true has to imply P1, and then true is always going to be true, but which means that value of P1 has to be equal to 1. So we make a revision. And then that revision say, okay, now P1, the value of P1 should be equal to 1. Now, so you can see that initially we start with the smallest assignment and we make it larger. And then now if P1 is equal to 1, and that activates this third clause in the formula. The third clause say P1 is equal to 1, P2 also has to be equal to 1. So we make a revision here. I said this is equal to 1. So that take care of this third. And then we look at the remaining one, and then the remaining formula doesn't say anything. So it doesn't really forces us anything. And then one property which we're gonna show later is that now if you reach this point, it is okay to say, okay, I mean, this is the satisfying assignment for this whole formula here. And that's okay because we are dealing with only whole formulas. Now let's repeat the same thing for the second case. So in the second case, we set P1 to be equal to 0, P2, 0, P3, 0. Now, because of the first formula, first clause, we revise it to P1 to be 1. Because of the third clause now, because P1 is now equal to 1, P2 also has to be equal to 1. Now the additional clause that we have, which the fourth one, say if P1 and P2 are equal to 1, P3 also has to be 1. So we replace it P3, the value of P3 to 1. Now at this point, we are in a situation where we can't really make this second clause to be true because P2 and P3, both of them are equal to 1. And then but the right-hand side of the implication is always false. So we can't really make this formula true by revising anything that we have. So if we reach at this kind of stage, then we can say, okay, for this formula is unsatisfiable. So this is how the satisfiability checker for whole formula works. If we write everything in terms of this implication form, start with the smallest assignment, which maps all the propositional variable to 0. And then you look at each clause, and if that clause forces us to replace value of propositional variable from 0 to 1, it does it. But at some point, it finds some clause which it can't satisfy by changing value of propositional variable from 0 to 1. You stop and say unsatisfiable, and so on. So that's how this algorithm is working. Let me tell you a bit more about this algorithm. Right. So here's a description. The general idea, which I already explained, it's maintain an assignment that for the propositional variable starting with p is equal to 0, and all the variables are mapped to 0, and then it updates the value of propositional variable from 0 to 1, if forced by the formula that we have, until either the entire formula is satisfied or contradiction is reached. So this is the description of the algorithm. Here I use some different representation of the assignment. Instead of writing assignment as a map, we use a set of propositional variable which will be mapped to 1. Okay, so this T corresponds to A on the above, and then initially T is an empty set. That's because our assignment is going to map all the propositional variable to 0. Okay, so when we say T does not satisfy F, we really means assignment corresponding A does not satisfy F. So then we repeat this process. We look at the reason F does not satisfy F is because one of the clause is not true. Okay, if all the clauses in F are true, are satisfied, then we are done. So there has to be some unsatisfied clause. Because F is in the whole clause, each will have an implication form. P1 and so a bunch of propositional variable implied G, where G is either false or another variable. Okay, and then this formula, T doesn't satisfy this clause means P1 up to Pk, they are all true under T, but G is not true. Okay, so if G is a variable, in that case, we increase t by adding g. So this corresponds to flipping the value of propositional variable from 0 to 1. But if g is false, then there is no way to satisfy this clause. So in that case, we return unset. And this is how this algorithm is working. Okay. So yeah, so then let's look at some analysis of the algorithm. So the analysis of the algorithm, the first question is why this algorithm is true, is correct. Okay. So let's see that where the potential, if you ask questions like this, then I think the first step is to actually feel where things may go wrong. Okay. So there are some obviously correct cases, and there are some cases where this algorithm potentially does something very strange and something incorrect. So first, identifying that possibility is the first step to understand this algorithm. Okay, what's the first things that can go wrong? The first step that can go wrong is that this algorithm may go on forever. So the algorithm should terminate, and then this algorithm may go on forever for into the infinite loop. So that's the first things we have to make sure doesn't happen. The second possibility is even when this algorithm terminates, okay? So if the algorithm terminates by getting out of this loop and returning this t at the end, then there are no problems at all. So it finds some t that satisfies this formula f, okay? So if we find some assignment that satisfies formula f, and that's a satisfying assignment, so we have nothing to complain about. So this algorithm proved or found some satisfying assignment, no problem at all. But there is another case the algorithm terminates, which is the algorithm might terminate by returning this unset, okay? But for this unset case, we can't really check easily whether it's really unsatisfiable or not. So there may be a case, this algorithm f return unset, but still the formula f is satisfiable. So what we have to prove when we argue the correctness of this algorithm, we have to make sure two bad things doesn't happen. The first, it doesn't go into the infinite loop. Second, whenever this algorithm returns unset, this formula f is actually unsatisfiable. So these are the two things that we have to, in a sense, the proof of correctness has to show. So here's how the proof go. So it's a reminder of how to read T as an assignment. Let me just change this to the blue. So the reminder is that T is a set of propositional variable, but really what we mean by this is the assignment. Okay, if some propositional variable P is in T, we are thinking about assignment that maps P to 1. If P is not in T, our assignment is going to map P to 0. Okay, so T is some encoding of an assignment. And we talk about this order between assignments where, and that's really you can say it's a pointwise order, or it's defined as you see on the screen. Okay. Now we want to argue it terminates in polynomial time. And why is that? Then the reason is whenever the algorithm actually goes through the loop. So let me show you the algorithm here. Here is an onset algorithm. Okay. So I put the algorithm here so that you have if you want to look at it, then you can see on the right-hand side. Okay, so why this algorithm terminates in polynomial time? That's because whenever this algorithm, it's an iterative algorithm, so it will go through the loop. So the loop that you see on the right-hand side of another file. So if it's gonna go through the loops, and so to show this algorithm terminates in polynomial time, we have to just show that the loop doesn't really happens many times. So we can do this very easily by saying, it's because whenever this loop goes through, so then loop iterates and come back to the beginning, that kind of thing happens only when the set T get increased by 1, okay? So this formula that you see on the right-hand side is not satisfied because G, I mean the variable case G, the variable G was not in the set T. And then in the body of the loop, G gets included in the set T. Okay. So whenever this loop goes through without really returning on set, this set T is gonna be increased. But in the propositional logic formula, we have only n variables. So this entire loop iteration is going to happen only n times. And then body of the loop, yes, it may take a linear time, but that's again polynomial. So this algorithm terminates. And then furthermore, the time complexity of this algorithm is going to be polynomial. Okay, just to say it again, algorithm terminates. That's because each time when it goes through, the loop goes through, it make a progress in the sense that set T gets increased by 1. And then the progress can happen up to the set T becomes equal to n. So this entire loop is going to be executed most n times. The execution time of the body of the loop is most linear. So things will take only polynomial time. So they take care of the first concern that I raised in the previous slides. Now, what's the second concern? The second concern is it really going to be correct? Is when it, especially when it return onset, is it really going to be unsatisfiable? So that's the real question. And then I want you to think about this. Okay. And then to show this, we can use so-called the loop invariant to show, I mean, that's actually the case. Okay. Now suppose, so what we're gonna show is that if formula F is satisfiable, okay, so if there is some assignment B that satisfies F, then we have to show that this algorithm will never return onset. So that's what we have to show. I mean, to prove if algorithm return onset, this formula F is onset. Okay, I mean, we showed the so-called contrapositive. In Korean, it's called 대우. So we showed that if F is satisfiable, then my algorithm will never return onset. So that's what we have to prove. And then to show this, we have to use, we assume that exists some assignment B which satisfies F. And then what we're gonna show is that our algorithm will maintain loop invariant. So the assignment A, which corresponds to T of the algorithm. So whenever we have a T, there is a corresponding A here, which is defined in this way. So defined by this relationship. So that A and this A, and then all of these are all related together. So they, yeah, right. So this A is gonna keep changing because the T is going to be changed again and again. But it will always satisfy this condition that A is always smaller than equal to B. So that's the condition which will always going to be true. And then so that can be shown by using so-called loop invariant technique. So then I have two exercises, which I want you to do. Maybe I'll give you about 10 minutes to think about this. So the first is to show this is actually a loop invariant. Second thing is to show that if this is, second thing is that by showing this is a loop invariant, this is actually a loop invariant, implies that my algorithm will never return onset in this case. So it implies the correctness of the algorithm. So to show that solve these two exercises. Now, if you have no idea what loop invariant is, so loop invariant is some property. So if you have a loop like this, some property which will be true, okay, so some property, I'll call it phi, which will be true when we reach the loop for the first time. So right after this assignment, this phi has to be true. And then another thing this loop invariant has satisfies that if the loop invariant phi is true, and if the loop condition holds, T in this case does not satisfy F. So if these two things are true, and under these conditions, we consider the execution of the body, loop body. Okay. So So then t will change, and then something that appears in phi may change as well. But after the execution of the body, phi will remain to be true. So some people call it as an inductive invariant. So it's a bit like an induction. We have to show that in the beginning, when we reach the loop for the first time, which is right after the initialization, this loop invariant phi is true. And then another thing we have to show is that it satisfies so-called a bit like an inductive case, which is if phi is true, loop condition is true, executing the body of the loop will make phi true again. Okay, so that's if these two properties are true, phi is called invariant. Loop, the inductive invariant was sometimes just called loop invariant. And then that kind of a loop invariance, if you show both of them, that implies phi is going to be true all the time whenever we reach this loop, because it's going to be true in the beginning and it's going to be maintained by the body of the loop. Okay. So to solve this exercise number 1, you have to prove these two things. First, you have to show that phi is true in the beginning. Second, you have to show that if assuming phi is true and then t does not satisfy f, you have to show phi is again is going to be true. So now phi here is going to be talk about properties of t before executing the body. Phi here is going to talk about properties of t after executing the body. Okay, so I will give you 10 minutes to think about this. 감사합니다. Yeah, so actually, although I said 10 minutes, maybe it's just, I think either you solved it or I have no idea what to do. So I think maybe better to explain it now. Okay, so here's how you can prove this. So erase this part. Okay. So we have to show that the two things that you see here. I mean, that we have the invariant in our case B. The statement in our case is that the A, which is obtained from T. So I'm gonna sometimes write the subscript T or maybe not, is always less than equal to B, which is a satisfying assignment. It's a satisfying assignment of F. Okay, so B is a satisfying assignment. Our assumption is that B exists, and then we are assuming that A is less than equal to B. Now, in the beginning, this is true. That's because T is after this initialization, so the base step, number one, we have to show after initialization, this is true. That's because after initialization, T is equal to the empty set, which means the A of A is going to map everything to 0 for P. So that's therefore A is the smallest element. Maybe so A is the smallest element of P. And then now for induction case, we argue we have to assume that A is less than equal to B. But then the another assumption is, this A doesn't satisfy F. Satisfy F. So, okay, so in this, also we know B satisfies F. Because A doesn't satisfy F, it's always possible to pick a clause. So that in the example, the clause was P1 and body of the loop, it was PK to G. Now we are arguing the first, our claim is G can't be false. Maybe this is a okay. So G cannot be false, and that's because G cannot be false, and that is because we know B satisfies formula F. B satisfies formula F, and A is less than equal to B. Now that means that B is in particular is going to satisfy P1 and PK implies G. At the same time, because A doesn't satisfy this P1 and PK implies G, that means so this A is going to satisfy this guy. Because B is greater than equal to A, B also is going to satisfy P1 and PK. That's because of this fact. And then, I mean, the choice of coming here. So now if you combine this second line and the third line, you can say B had to satisfy G. So that means G cannot be false. So now G is not equal to false. So G should be a variable. And then now because B satisfies G, and including this variable G inside the T, is not going to change this order relationship. So if you set A where this G, variable G is now going to be mapped to 1, this is still going to be less than or equal to B, because B also is going to map G to 1. So that shows the invariant holds after the iteration of the loop. So we show that, I mean, so this number 2 is also satisfied, right? We assume invariant is true. We can also assume that the loop condition is true. And then under that assumption, we said actually the executions will go until the end of the loop without returning. And then the final outcome is also going to satisfy the loop invariant. So that's what we proved. So these two, 1 and 2, implies V is a loop invariant. And furthermore, because I mean our proof of this number 2 actually implies that if the invariant is true and then this T does not satisfy F, then this return will never happen. So because what we've shown here is that this G cannot be equal to false. That's what we proved here. So this return is not going to happen, which means that if there exists some assignment B which satisfies F, then we will never hit this, yes. Okay, so if under this assumption, invariant assumptions, under these invariant assumptions, we will never hit this case. That's because of, that you see on the left-hand side, in that case, G will never be equal to false. So that's why we will never hit this case, which means it will keep going on and then eventually return some satisfying assignment T. Okay? So that implies if there exists a satisfying assignment, then this algorithm will terminate and return a satisfying assignment. Furthermore, this loop invariant that you see here implies something very strong. Is say that if there is a satisfying assignment of F, this algorithm will return the minimal or smallest satisfying assignment according to this less than or equal to order. Because of this because of this kind of shows that if formula is satisfied, then there exists a minimal satisfying assignment, and that's the property that's in some sense exploited by this algorithm. Okay, let's clear all of this. Then, okay, so if you have any questions in while I'm explaining this, maybe you can raise your hand or maybe ask a question anytime. Okay. Now let's move on to the other part. So second class of formula that we will consider is so-called the 2CNF formula. That's a conjunctive normal form formula where each clause has at most 2 literals. So sometimes these 2CNF formulas are called Chrome formulas. So for instance, so we're gonna, so I didn't really include any examples, but I think the definition is quite clear. It's a conjunctive normal form formula where each clause will contain at most 2 literals. Okay, if it contains 3 literals, then it's not a 2CNF formula. And we're gonna to design an algorithm for this 2CNF formula. We'll introduce a few notation. The first notation is this L bar, sometimes called complement of literal. And that is essentially putting a negation, but we'll remove double negation. So if the literal is already a negated form, but we put negation here again, and then we get rid of double negation, so we will get P. If the literal is just propositional variable, then we will put a negation there. So it's just what you expect. It's a user complement operation. And then now for if we are given a 2 CNF formula, then we can construct something called implication graph. Okay? So the implication graph is a graph, directed graph, where the vertex of the implication graph are propositional variable that appears in formula F and their negations. Okay, so in some sense, all the possible literals are the vertices of the vertices of this implication graph. And then we put an edge between the two literals in this graph if the formula contains essentially an implication that goes from L to M. And because it's written as a disjunction, it can be written as this not L or M. So that is, yeah, so this is really, L implies M, written as a logical form. And then, or maybe it doesn't really matter whether not L appears as a second disjunct or first disjunct. Right. So to check your understanding, let me ask you this question. So I will give you maybe 1 minute to think about this. In this, suppose we are given 2 CNF formula F, and then we constructed this implication graph. Now, suppose we have an edge that goes from literal L to literal M. Now, my question is there also going to be an edge from literal negation of M to negation of L? Maybe doing some poll here. Okay, so this is the outcome of the poll, and the answer is yes. In this case, that's the reason is because in Korean it's called 대우. So this, if you have if L implies M, sure. Yeah, if L implies M, then what we do know is that negation of M implies negation of L. Okay, so negation of M, and by using the notation that we have, is corresponding M bar, this corresponds to L bar. So if the L implies M is true, then we are expecting M bar implies L bar also should be true. Okay, and in fact, you can also read it from the definition of an edge in this case, because if I write it as a, as a disjunctions, this is going to be not of L bar or M bar or L bar, but that's the same as M or negation L bar. Okay. So that's exactly the condition of L implies, the edge from L to M exists in the graph. So if there is so this means always it has some kind of duality property. If there's an edge that goes from L to M, then there's always going to be an edge from M bar to L bar. Okay, so here is an example of this implication graph. So it's a bit complicated, but I will just show you, kind of emphasize only one thing. If you look at P0 or P2, so first, all the vertices are either propositional variable or their negation. In some sense, all the literals and all the possible literals that can appear in the formula, they are the vertices. Okay, and now for each of the clause P0 or P2, it generated two implications. One is not P0 goes to P2. So we have a not P0 goes to P2. Another is that it's a contrapositive in Korean, it's called 대우, which is not P2 goes to P0. So we have not P2 goes to P0. So it always comes in pairs. Okay. So then it turns out for two CNF formulas, satisfiability can be reduced to some kind of algorithmic questions on graph. So especially it corresponds to some form of reachability problem on implication graph, and which most of the reachability problem on implication graph can be solved in polynomial time. We can repeatedly apply Dijkstra's algorithm, or you can use Bellman-Ford algorithm, or some of the algorithms that you learn in the algorithm course. If you don't remember, you can accept my wording, which is reachability questions for graphs can be solved in polynomial time. So it's not that difficult problem in some sense. So, but it turns out satisfiability for two CNF formula can be reduced to the reachability problems of implication graph. And the key concept behind this reduction is so-called consistency. And this consistency is say something like this. If we say implication graph is consistent, if there is no propositional variable P, such that, so you say this kind of propositional variable P shouldn't exist if the graph G should be consistent. And this bad propositional variable P has this property, which is it has a two path. One goes from P to its negation, and another goes from its negation to P. Okay, so if my graph G has this is a cycle, so where we have a propositional variable P and we have a path that goes from P to its negation, and then also we have another path that goes from its negation to P. We say this graph is inconsistent. If there is no such a cycle, then we say this graph G is consistent. Okay. Then the main key theorem here is that 2CNF formula F is satisfiable precisely when its implication graph is consistent. So then this consistency can be checked by reachability. It's really about reachability between P and its negation. So, which can be done in polynomial time. So if this theorem is true, then the problem of checking satisfiability for 2CNF formula can be solved in polynomial time by using this reachability. First constructing this implication graph, and then checking some reachability property over this implication graph. Now, why this theorem is true? Then the implication side is the one side of the implication is quite easy, and the other side is a bit hard. So likely we have to talk a bit more about the other side of the implication in the next lecture. Because it's difficult, let's just, I say a bit today and then again the next week, and then on Wednesday. So the one side, which is this implication, this only if direction, which is formula is satisfiable, then it is consistent is easy. I mean, the proving this is easy. That's because, I mean, if we consider contrapositive, say, so showing satisfiability implies consistency is the same as showing inconsistency implies unsatisfiability. Okay, we just take a contrapositive of this this implication, and then so what we have to show is if G is not consistent, then we have to show formula F is unsatisfiable. So suppose G is not consistent, and suppose the formula F is satisfiable. Okay, so G is not consistent, but formula F is satisfiable. Then because of inconsistency, there are paths. There are propositional variable P, and there are paths that goes from negation of P to P, and P to P is its own negation. But because this graph G essentially encodes implication, that means from propositional logic formula F that we started with, so propositional logic formula F we started with, we can prove negation of P implies P, and the P implies its own negation. So F from F, it follows that negation of P, I mean, I think they're using more formal notation. Using formal notation, what it says, we F entails negation of P implies P, and also F entails P implies negation of P. Okay. But then because, so now we can, by looking at this, if the assignment A satisfies F, so then assignment A also has to satisfy this guy, this implication, and then the other implication. The implication below, that the fact A satisfies the implication below, that gives us, I mean, this order relationship. Okay, I mean, just from the semantics of the implication. And then the implication above gives another order relationship. But this cannot happen. I mean, assign this A assign either 0 or 1 to propositional variable P. So, I mean, both of this really means A of P is the same as A of negation of P. That cannot be true because this also always have to be equal to A of 1 minus A of P. Right. So this leads to a contradiction. So that shows, I mean, the if formula is satisfiable, then implication graph is implication graph is consistent. Okay. So this direction is easy. So in some sense, this is what we've shown. But the other direction is a little bit difficult. It involves some algorithm. So that's what we'll focus on. I will say a few words about this, and then I will continue next week. Okay. So actually, the other direction is done. I mean, the proof of the other direction is an algorithm. Okay. So I will tell you about this algorithm in the next slides. So here's how the algorithm works. So I'm expecting that you don't understand this algorithm at all, but my feeling is if you hear it twice, somehow you will understand it. So the algorithm works like the one before. We initially have a bit like one before, but it's a bit different. So initially it say A is a partial assignment, which means it doesn't assign anything. But so given the propositional logic formula F, which we know that its implication graph is consistent. So what we have to prove is consistency implies satisfiability. That's what we're gonna do. So what we'll do is that assuming the implication graph is consistent, we will construct satisfying assignments. So we are given formula F, whose implication graph is consistent, and our job is to produce satisfying assignments. So here's how it does it. So initially it sets the A, which is a partial assignment. So it doesn't assign anything. So it's really an empty map. Okay. So initially, this A is an empty map, doesn't assign anything. But then if it assign somehow inside the loop, it assign, we pick one variable and assign some value to the variable. So if we go through this loop n times, assuming there are n variables, then we are done. Then this A is going to be returned as a satisfying assignment. So the whole thing, all the important bit is done by the body of the loop. What the body of the loop does is that if A doesn't assign some value to some propositional variables, let's call it P. Let's call it P1. Okay, so we doesn't assign propositional variable P1. So then the first step the algorithm does is it tries to check whether there exists a path from P1. So in the consistency, say one of these paths doesn't exist. So if we have a path from P1 to negation of P1, negation of P1 to P1, so then this implication graph cannot be consistent. So consistency say either the one on the top or the one on the below, or both of them doesn't really exist in my implication graph. So pick the literal L such that the path doesn't exist. So assume that in this case, what doesn't exist is the one below. So the one below doesn't exist. So in that, after finding this, what we do is we pick the value of propositional variable so that this part has a value 1 and this part has a value 0. Okay. So then in this case, it means P1 has a value 0. I mean, that's what this assignment tells us. And after doing this assignment, we have a go to the inner loops. So A now get extended. So A has a P1 gets mapped to 0. So then we go to the inner loop, and now we look at the implication graph. And then implication, by looking at using A, we can label all the vertices, I mean, not all, but some vertices of this implication graph to value 0 or 1. For instance, our implication graph will have a P1 and negation of P1. And then after this assignment, P1 will be assigned to 0, P2, this guy will be assigned to 1. But maybe it might have a P2 and negation of P2. Some of them is not going to be labeled at all. Some others like P3, negation of P3. And these guys may be already labeled in the previous iteration like a 1 and 0. So you look at this partially labeled graph, implication graph, and then look at edge, where the edge goes from so suppose if we have an edge that goes from 1 to something which doesn't have any value. And this is something which doesn't have any value will now get assigned to 1. If we this P2 to assign it 1, so then this corresponding its dual version to negation of P2 will get assigned to 0 and so on. So you keep doing this until we can't go do anything further. And then we go into the outer loops. So this is a nested loop algorithm. And it turns out if you could keep doing this, then you will always be able to find the satisfying assignment. So I will talk more about this algorithm of constructing satisfying assignment from consistent graph, and then the correctness of this algorithm on Wednesday. Okay, so that's it for today, and I will stay until 10:20. And if you have any questions, you can ask me. Okay, so thank you very much.